Today's lesson is on segment proofs, specifically segment proofs where we're using the segment addition postulate. So we've dealt with algebraic proofs. We did an introduction for geometric proofs where we had some geometric properties tied in with our algebraic proofs. Now we're going to look at strictly geometric segment proofs, okay? Almost all of these proofs is going to involve this segment addition postulate. So just to review, the segment addition postulate tells us that if points A, B, and C are collinear, and point B is between points A and C, then the measure of AB plus the measure of BC equals the measure of AC. Now, with our segment addition postulate, notice that we're talking about the measures of these angles. So we're in that equal sign notation, okay? With our introduction to geometric proofs, we had to convert some segments being congruent into the measures of the segments being equal using that definition of congruence over here. We're gonna see that same thing in today's lesson, where we're going from that congruent notation to equal sign notation and then equal sign notation to that congruent sign notation, okay? We are going to use the definition of a segment bisector. So if you have a line, a ray, a segment, a point that bisects a line segment AC, if point B is where that segment is being bisected, then segment AB is going to be congruent to segment BC. Okay, and we saw the definition of midpoint before. If M is the midpoint of segment AB, then segment AM is congruent to segment MB. Okay, so let's start getting into our segment proofs. Okay, just like with those geometric proofs, the first two proofs are going to have the statements done for us. We're going to try to come up with the reasons as we get a feel for what these proofs look like. And then on the back page, the last three examples, we're going to try them on our own. So our first proof is a pretty classic example for the segment addition postulate. So we know that segment AB is congruent to segment YZ. So a part of our segment is equal to a part of another segment. And then segment BC is congruent to segment XY. So we have that other piece is congruent to the other piece. And we want to try to prove that segment AC is congruent to segment XZ. So we want to prove that the whole segment is congruent to the other whole segment. Okay, so our first statement is simply our given. Okay, that's always the first step in your proof, right? And with these segment proofs, you should know going into it that there's a very good chance you're going to use the segment addition postulate. So right away, I am going to convert my congruent sign notation over to my equal sign notation using the definition of congruence. Okay. Next, I'm going to use my segment addition postulate. Okay, so AB plus BC equals AC, and XY plus YZ equals XZ. I put those two equations in the same step because I'm using the segment addition postulate for both. You could put it in two different steps. I just like to keep it in one. It's fine either way. Okay, now this is where we're going to get into our substitutions. If you have a highlighter or anything like that, colored pencils, I think color coding these is very helpful. So I'm going to take a look at this first segment addition postulate equation. AB plus BC equals AC. And if I look at line 2 tells me that AB is equal to YZ. So where I see AB in my first equation, I'm going to substitute in YZ. Okay? So between step 3 and 4, I am going to manipulate this boxed equation here, okay? So I changed AB to YZ because I knew that those were equal. Now, I know that BC equals XY. So where I see BC, I'm going to do the same thing. I'm going to substitute in XY. All right. Now, I don't know anything about AC, so I'm going to leave AC as is. All right. So between step 3 and 4, I used substitution. Okay. Now, I'm going to erase those boxes there. Okay. If you look at step 4, all right, I have YZ plus XY. If I look at my second equation from step 3 for that segment addition postulate, I also have XY plus YZ. Okay, that's the same thing. XY plus YZ is the same thing as XY plus YZ. So I can use a special case of the substitution property, right, that transitive property, to cut out the middleman, right, cut out what I highlighted in yellow because that's the same thing, both of those lines, and say that XZ equals AC. So that's an example of the transitive property. Okay. Now, if I look at my proof, okay, my proof is back into that congruence symbol notation. So I'm going to have to go back to that congruence symbol notation, right? So if the measure of segment XZ equals the measure of segment AC, then I know segment XZ is congruent to segment AC using the definition of congruence. And then finally, I can use the symmetric property to flip my congruence statements there. So that's my symmetric property, okay? I didn't put the transitive property and symmetric property up here in those common justifications, but you are going to use them over and over again in these proofs. So you want to make sure that you are keeping up with all of those justifications and properties. Okay, so we started with this piece plus this piece, or I'm sorry, the pieces being congruent, and we were able to prove that the whole segments were congruent using the segment addition postulate and some substitution there. Now, number 2 is going to be similar, just a little bit different. Okay, so if I look at my given information, I see that segment LM is congruent to segment OP, and then segment LN, which is the whole segment, is congruent to OQ, which is the whole segment. Okay. I want to prove that PQ is congruent to MN. All right. So now I know the wholes and one of the parts are congruent. I want to prove the other parts. Okay. So my first statement is my given. All right, my second statement is where I'm going into that equal sign notation. So I'm using the definition of congruence. All right, and then I'm going to use my segment addition postulate, see what substitution I can use to try to manipulate my equation. So step 3 is that segment addition postulate, where LM plus MN equals LN and OP plus PQ equals OQ. Okay, now I'm going to take that first equation, all right, and I'm going to try to use some substitution here, okay? So LM equals OP. Looking at this first statement, LM, I'm going to substitute LM for OP because I know that those are equal. All right, the next piece is MN. I don't know anything about MN right now, okay? So I just leave MN as MN. And then I get to LN. LN is equal to OQ, so I am going to substitute in OQ there. All right, so I'm taking that first equation and I'm just doing some substitution and seeing what happens. All right, so I've did some substitution. and I'm going to get rid of those boxes. Okay. If I look at my equation in step 4, all right, that's equal to OQ. And if I look at my second segment addition postulate equation in step 3, I see that they're both equal to OQ. OP plus PQ equals OQ, and OP plus MN equals OQ. All right, so this is an example of my transitive property. All right, think of this as cutting out the middleman. We can say OP plus PQ equals OP plus MN using the transitive property. All right. Now, if I look, I have OP on both sides. So I can subtract OP from both sides, and then I'm just left with PQ equals MN. So this is my subtraction property of equality. And then to get to my prove segment PQ is congruent to segment MN, we're going to use that definition of congruence again. Okay? All right. Okay. Now, on the back, like I said, we're going to do from start to finish our statements and reasons. So, forgot a little line there. For number 3, I'm given that H is the midpoint of segment IK and segment JL, and that segment JH is congruent to segment HK. So I'm going to mark those off in my diagram. Segment JH is congruent to segment HK. And list my given information. And JH is congruent to HK. Okay. Now, I want to try to prove that HK is congruent to HL. So I want to try to prove that these two segments are congruent. Okay. Now I highlighted in there, I didn't mark them off as being congruent because it's just what I'm trying to prove here. If I look, I know that JH is already congruent to HK. I know that H is the midpoint of segment JL. So if H is the midpoint of segment JL, then JH has to be congruent to segment HL. Okay, so JH is congruent to HL by the definition of a midpoint. Now, I could also say that segment IH is congruent to segment HK by the definition of a midpoint because I know this point H is a midpoint of both segments, but I actually don't even need to put that in my proof because I already have enough information at this point to prove that segment HK is congruent to segment HL. All right, and that's by using that transitive property. So if HK is congruent to JH and JH is congruent to HL, you can think of that as like cutting out that middleman there, and we can say that segment HK is congruent to segment HL by the transitive property. Okay? All right, so this is one where we actually didn't need to use the segment addition postulate. This was just a nice transitive property proof. Okay, let's take a look at number 4 though. Number 4 tells us that S is the midpoint of segment RT. All right, so that's my given information. S is the midpoint of segment RT, and that is given. So by the definition of a midpoint, I know that segment RS is congruent to segment ST. Okay, that is the definition of a midpoint. So I'm going to mark that off in my diagram. Now, right now, if you're kind of feeling stuck, think about your segment addition postulate, okay? I see that what I'm trying to prove here has an equal sign, so I'm probably going to need to get into that equal sign notation. When you're thinking of that equal sign notation with segments, think of that segment addition postulate. So I'm going to say that RS plus ST equals RT. So RS plus ST equals RT by the segment addition postulate. Okay? In order to do any substitution, I actually need to put in that RS equals ST by the definition of congruence. You could have done this before the segment addition postulate. You could have done this after. That specific order doesn't matter. All right? But you have to have this step in here before we do any substitution. So now that I'm in my equal sign notation for the measure of segment RS is equal to the measure of segment ST, I can substitute in, all right, and I want to look at my proof to see where I'm trying to go with this. I want to show that RT is equal to 2 times the measure of RS. So I'm going to take this ST and substitute it in with RS, okay? So I'm going to say RS plus RS equals RT, and that's by substitution. All right. Now, just like if I'm thinking of just basic algebra here, x plus x equals 2s. So RS plus RS equals 2 times RS. All right, it's not addition because I'm not adding anything to both sides. This is, again, substitution. I'm just combining like terms here. All right, and if I look, I'm so close to what I'm trying to prove. All right, I just need to use that symmetric property so that RT equals 2 times RS using the symmetric property. Okay. All right, we are almost done. We have one more proof. All right, this one is a little bit longer. This is probably the trickier one out of all of these. So let's look at proof number 5, okay? It tells us that point C, bisects AD. All right, so this AC is going to be the same as this CD. I'm just kind of thinking ahead here. And then B bisects AC. All right, so let's list that given information. So C bisects segment AD and B bisects segment AC are given information. Okay. By the definition of a segment bisector, all right, like I said, AC is going to be congruent to CD. And AB is going to be congruent to BC. Again, once I state those segments as being congruent in my proof, I also want to put it in my diagram. I want to notate that in my diagram. So this is the definition of a segment bisector. Okay. I know that I'm going to have to use this segment addition postulate, kind of thinking ahead. So I'm going to use the definition of congruence now, just to say that AC equals CD and AB equals BC. Now, if I use my definition, if I use this segment addition postulate, there's actually a couple different segment addition postulates I'm going to use here. All right. First, I'm going to say that AB plus BC equals AC. Okay, that's the first segment addition postulate I'm going to use. Okay, and I know that AB is equal to BC. And if I look at my proof, I'm trying to get this whole segment AD all in terms of AB, right? So I'm trying to show that this whole segment AD here is 4 of the lengths of those AB. And you can kind of see that in the diagram, all right? But we just need to formally prove it. So if I say that AB plus BC equals AC, I can use this substitution here. I know that AB equals BC to substitute BC. So AB plus AB equals AC. So this is substitution. And if I simplify this, 2 times AB equals AC. Okay. Now, I'm going to say that I'm going to use my segment addition postulate to say AC plus CD equals AD. So AC plus CD equals AD using the segment addition postulate. All right, and I'm going to use some substitution again. All right, so for step 8, I'm going to go back. I don't want to use that color. Let's use green here. So CD was the same as AC, right? So I can say that this is AC plus AC equals AD. Using substitution. So this equation is 2 times AC equals AD using substitution. So 2 times AC is equal to 2AB. All right, and that, again, this is a lot of substitution. Comes from right here. AC is equal to 2AB. And in my last step here, 4AB equals AD. So this was substitution. And then we have substitution again. Okay, there's a couple different ways that you could have done the segment addition postulate and substitution to do this proof. All right, this is just one of those ways. It's a lot of substitution and segment addition postulates. So like I said, this isn't the only way that you could have done this. All right, maybe you thought of another way that was a little bit shorter or that made a little bit more sense to you. But that is our lesson on segment addition postulate proofs and segment proofs. Thank you so much for watching. If you have any questions, you can comment below.